the FDA.
Great. Thank you, Michael, and thank you to the organizing committee for this whole day session and for inviting me to present. Just to note that I'll be presenting here on behalf of the entire OMOP research team, and also everything that I'm going to present, including this presentation and all of the data that I'll be sharing with you, is all publicly available on the OMOP website. What I actually want to talk about today is a bit of a framework for thinking about how we can go about measuring bias and how we can quantify how well observational studies are used, with the intent that not only can we use that information for context for interpreting observational studies, but also that we can use that information to potentially adjust and calibrate our estimates to be more in line with our expectations. So to do that, I want to use a motivating example just to ground us. This is a recent publication looking at the risk of GI bleeding associated with clopidogrel. And this was an observational study conducted in the General Practice Research Database. It was a nested case control study that was designed, and this is very typical of any observational study we would pull out of the literature. And as with most studies, we would go to the results to look at the effect estimate. And in this particular case, the authors found that clopidogrel increased the risk of GI bleeding with an adjusted rate ratio of 2.07 and a confidence interval that spanned from 1.66 to 2.58. So for those of you that are interested in the p-value, that's highly significant, less than 0.001. So in the context of today's discussion, the questions that I'm really prompted by are, how much can we believe that? Is that 2.07 actually meaning there's a doubling of the risk? Is that 1.6 telling us that that lower bound is in fact telling us that the risk is at least a 60% increase? So just in terms of terminology, one of the things that we've been trying to think about is how to classify this information from what we can learn from observational studies. So specifically, when I think about error, I'm thinking about the distance from the point estimate to the true effect, which is inherently unknown. So in this particular case, I'm asking the question, how far away is that estimated 2.07 from whatever is the true value? Bias, which is the topic of our talk, is actually really about the expected value of that error distribution. So I could frame that as, if I were to apply this same type of analysis to this same type of data for this same type of outcome, how far on average would those estimates be from their truth? And we heard about uncertainty from Steve's talk earlier. One of the things that we've been focused on is thinking about coverage. So specifically, what is the probability that a true effect is contained inside of that confidence interval? So one way to think about this, if I apply the same type of case control study to this same type of electronic health record data for this same GI bleeding outcome, do the 95% confidence intervals that we generate from our studies, do they actually contain the true answer 95% of the time? So Sebastian mentioned this paper, and it was in the pre-reading, but there's a lot of discussions about how we could use negative controls as a way to validate what we've observed in any particular study. And the authors in this paper effectively suggest that in addition to your target outcome, you could take a handful of negative controls, and if you looked at those negative controls and they didn't purport to find the same outcome, maybe in some qualitative way you'd feel better about the plausibility of your effect. What we've been doing in OMOP is thinking about how could we take this idea and apply it systematically to instead take a large sample of both negative and positive controls to be able to empirically measure an analysis operating characteristics, and then to use the information we gain from that measurement to calibrate our study findings. So just to give you a very specific example here, the way that we've gone about doing our research to study methods performance is first start by developing a standardized implementation of an analysis strategy. So to use that motivating example, we implemented a nested case control study with a standardized approach to matching cases and controls with a standard set of inclusion and exclusion criteria. In our particular case, our standard approach that we applied to a large U.S. administrative claims database yielded an estimate similar to those that the authors found for clopidogrel and GI bleeding, where we observe a 1.8 with a narrow confidence interval, due in large part to our larger data sample size. What we then did was take that same standardized implementation of that method and applied it consistently across a network of databases to a large sample of negative and positive controls. So specifically for GI bleeding, We identified 24 drugs that we believe are associated with drug exposure, and 67 drugs for which we could find no evidence to suggest that the drug might be related with GI bleeding based on labeling and literature. And effectively what we've done is by running that method across all of those negative controls, we can actually measure what are the effect estimates we observe for those negative controls and use that information to then measure how biased the analysis method might be. And the assumption we're going to make here is that for a negative control, we don't know what the true value is, but based on lack of evidence, we can assume that the true relative risk is 1, and therefore we can measure how far away are our effect estimates from that 1. So what I'm showing you here is a forest plot that's showing you the 60 some odd estimates for negative controls using a case control design for GI bleeding in a large claims database. And just a couple things that I want to highlight. So basically on your y-axis here, you're seeing all of the drugs. On your x-axis, you're seeing the relative risk. And every estimate there, that's a point estimate and a 95% confidence interval. And just the color coding very briefly is just the oranges are statistically significant and the blues are not. These are all negative controls. That means we would expect 95% of these estimates to contain 1. So one thing we notice is that there's some issue with calibration of the uncertainty. The other thing we notice is that on average these estimates actually tend to be shifted a little bit to the right. That is, there appears to be some sort of inherent positive bias in this particular method. So specifically, if we were trying to measure this, we can think about that coverage probability. We'd like our 95% confidence interval to have a 95% coverage. In this particular case, for this method, on this database, for this outcome, we observe that coverage probability to be 45%. One thing you could do is, this is a series of effect estimates, but what we could actually do is interpret that, in fact, as a distribution. That is, take those 60 estimates and fit a distribution to say, what is our expectation when we apply a case control design to this database? And what you see from this distribution is there's bias. That is, the expected value is greater than 1. There's also substantial variability. When applying this method to a negative control, we can get anything from a 0.5 to upwards of a relative risk of 3, which is exactly what Bob was mentioning earlier. So when we ask the question, well, how do we know when is an estimate reliable? One thing that we've been thinking about is how could we use this empirical null distribution derived from the data as the means of measuring how well this will work. So there are a variety of different measures that we could use to measure accuracy of a method. We've talked about bias. There's also mean squared error and coverage probability that I've mentioned. One of the challenges we have in measuring these is that we can only make assumptions about how are we benchmarking our estimate to truth. So we can assume negative controls are a relative risk of 1. For positive controls, we really can't assume what the effect estimate is, but here's where simulation could actually support our endeavors in learning about observational data. We might also be interested in measuring discrimination. That is, we have positive and negative controls, and regardless of what the effect size is, we'd really like to have observational studies that can discriminate between what are the true effects and what are not. And that's just yet another metric that could complement our efforts. We also could measure sensitivity and specificity. And the reason why I highlight this is translating an observational study into action. At some point, we actually need to get to a decision threshold to say, have we learned enough to act, yes or no? And the contention that I would make is that a real opportunity we have is to actually measure how reliable the information is from our studies, such that our decision makers can use that information as context for interpreting the results. So one of the things that we've been working on is trying to think about how can we gain information from these empirical studies to provide the context for interpreting a result. So what I'm showing you here, just to orient you, is a methods dashboard to trying to give us a sense of all of those performance measures. So just to orient you, every row here is a different method. So from top to bottom, I'm showing you the results of a new user cohort design, a self-controlled design, and a self-controlled cohort design. And the columns are different performance metrics. So that first column is showing you discrimination through an AUC or an ROC curve. That second column there is showing you error, which you can use to understand quantified bias. And that third column is showing you coverage probability, where what you'd like to see is that the methods had a 95% coverage, with only 2.5% on the left-hand side and 2.5% on the right-hand side. Now, what we've observed consistently in all of our studies is that depending on which method you choose, which database you apply, and which outcome you're studying, you're going to observe different types of error. And those errors are going to influence the way you interpret your results. Now, there's two directions we can go from this. One is to think about how can we improve our methods so that we don't observe this kind of error and that we don't see this miscalibration of our coverage. The second opportunity is to say, given that we've now learned about the bias, we've learned about the error that we can expect, how can we use that error to adjust the effect estimates that we've generated? So going back to my example here with this forest plot, that graph below is that empirical null distribution. So to Bob's original comment, is it credible to look at a case control study with an effect estimate less than 2? Well, this is suggesting there's a high probability that you could observe that relative risk less than 2, even if you were looking at a negative control. So one way to think about determining credibility is to use that empirical null distribution to set your bounds for when do you have something that might be actionable information. So you could actually think about, instead of having a theoretical null distribution based only on sampling variability, you could use the empirical null distribution based on the uncertainty that existed in your data source. And by doing that, effectively what you would do is, rather than saying 55% of your effects have a traditional p less than 0.05, you would actually see that you are closer to calibration. That is, approximately 5% of your effects would actually have 5% outside of those bounds. I'm not going to go through the details of the math, but basically the intuition that we've been working on about empirical calibration is, can we take that empirical null distribution down below and embed it into our analysis to adjust the effect estimate based on what we've just now learned? So intuitively, you could imagine that you've got an effect estimate. You want to move it to adjust for how much bias you observed, and you want to stretch out that confidence interval to deal with how much uncertainty you didn't account for based on sampling variability alone. Oops. So in that example of the political bleeding, pre-calibration, we had estimated an effect size with a confidence interval that went from 1.8 to 1.9. So we had believed that we had a very tightly coupled effect estimate. Post-calibration, after we accounted for this empirical null distribution, our effect estimate goes from 0.8 to 4.5. That means two things. One, it means we can't say that we had something statistically significant. But secondly, we also can't rule out the fact that the effect isn't larger than 2. What this is helping us do is account for the uncertainty to understand the amount of variability that we'd have in our estimate. Just as reference, I've provided a few slides here to show you exactly what happens to effect estimates as we go through this. So this is a series of specific drugs for GI bleed. This is pre-calibration on the left-hand side, where we have poor coverage probability, and post-calibration, after we apply that empirical null distribution. You see the effect estimates move, and now we have closer to calibrated coverage. And through our simulations, even as we inject signals of different sizes, we see this same phenomenon occur. What's important about that is the empirical null distribution is different for every method. It's different for every data source. It's different for every outcome that we want to study. And so one of the things that we've been trying to understand is, are there commonalities across that? But also, how can we develop efficient strategies for measuring that empirical null distribution so we can use it in the context of our results? Going back to our dashboard, this is what the dashboard now looks like after we have calibrated those estimates. One of the interesting insights about this is discrimination does not change. Our ability to discriminate between positive and negative controls remains the same on the basis of the rank ordering of our effect estimates. But now through calibration, no matter what the method was or the outcome, we're able to get a lower biased estimate with coverage that's more close to the nominal operating characteristics we hope for. So just to conclude, I think what we've started to learn and we're really excited by is that there's a lot of valuable information in observational studies. However, we might need to rethink how we interpret observational study results to really capitalize on the value of those databases. We think one approach for doing that is a systematic exploration of negative and positive controls, both to measure the operating characteristics of a given method, but then also to use that measurement to revise our estimates and to think about what is the true uncertainty we observe. I think where we are right now, we think there's a real opportunity to improve the methods for calibration, but to a large extent, I hope I didn't want to submit to for the discussion, that one of the questions we have to ask is, can we actually go about generating an evidence base for observational study interpretation? So with that, I'll stop. Thank you.
Great. That was fascinating. Okay, we're going to kick off this discussion by having some brief reactions and comments from a couple of our panelists. The first is John Wang, who is the chief of the Division of Clinical Decision Making at Tufts University.